Good morning, everyone. Okay, so what I want to do is finish up with MOSFETs today, and then hopefully, if we have time, get into a new component op amps. Okay, so let me go ahead and one thing about using specifically an N-channel MOSFET. If you're using an N-channel MOSFET, let me draw up the typical circuit. And as we said last time, this is referred to as low side switching. And low side switching because the MOSFET that's acting like our switch is on the low side of our load, whatever it is that we're trying to cause current to flow through it. So if this was a motor or whatever type of load that it is, the MOSFET needs to be down here. Now, I've said this before. Why? Well, let's go ahead and see what happens if it's not on the low side of this circuit. So if we were to place the MOSFET on this side of the load, this would be regarded as high side switching. Now, the determining factor as to whether this MOSFET is on or off is the voltage between the gate and the source. So let me put the gate here. Source and drain. And so its VGS needs to be greater than VGS TH, our threshold voltage. So, let's just go ahead and say that we're working with a 5-volt system here. So this will be 5 volts. We want this guy to be on, so I'll place 5 volts over here on the gate. And the gate source threshold voltage, that threshold that we need to cross in order for this MOSFET to be on, let's just say is 2 volts. Okay, and you may be looking at this and you go, well, we have 5 volts at the gate. Therefore, this should be on because 5 volts is greater than the threshold voltage of 2 volts. Here's the problem with that, which is it's the voltage between the gate and the source that needs to be greater than this threshold voltage. Well, what's the voltage at this point? You can break this down into the voltage at the gate minus the voltage at the source. Now, when you're doing this and you're using it properly with an N-channel MOSFET, it needs to be low side switching. This voltage on the gate is really all that you care about, because VS, I should say, VS over here is equal to 0 volts. So when you look at VGS, if we were to place 5 volts here, is just equal to 5 volts minus 0 volts, which equals 5 volts. So essentially in this arrangement, VGS is equal to VG. So not a problem when you're low side switching. But when you are trying to do high side switching, if this is on, then we have a voltage drop across this. So when we have 0 current flowing through here, we have 0 voltage drop across the load. And so you do have 0 volts at this point, and this is 5 volts. But once this turns on, now this ends up turning into 5 volts. Now, once you have 5 volts on the source, you now get 5 volts minus 5 volts, which means that VGS is now equal to 0 volts. And then this turns off. Once it turns off, then this goes back to 0 volts, and now VGS is equal to 5 volts, which is greater than 2 volts, so this tries to turn back on. When this turns back on, all of a sudden, now this 0 volts goes to 5 volts, VGS is equal to 0 volts, it turns back off. So in this arrangement, an N-channel MOSFET is not going to work. In other words, you can't do this. Okay, so we need something else. If you needed to do this, if you needed to put the MOSFET up here, you're gonna have to use a different kind of MOSFET, and I'll get into that. Now, in this type of simple arrangement, there's nothing wrong with using an N-channel MOSFET on the low side. In fact, for this circuit in general, there really is no difference between having there's no desire to do low side versus high side switching. But if you're going to use an N-channel MOSFET, you're going to have to do low side switching. So in order to do high side switching, we're going to have to use a P-channel MOSFET, not an N-channel. Okay, so let's go ahead and let's cover the P-channel MOSFET. It's going to behave very similarly to an N-channel MOSFET, with just a simple difference in how you calculate that the gate source voltage. Okay, so let's go ahead and let's set this up. We have a drain here, we have a source here, and our gate is up there, and then let's go ahead and attach our load down here. And now for a P-channel MOSFET. It is on when VGS is less than minus the gate source threshold voltage. Okay, so let's go ahead and set up our example over here. We're going to make this equal to 5 volts. Let's say our VGS for this MOSFET let's say it is equal to 2 volts, and let's say the RDS on value is 0.1 ohms. Okay, and so if we wanted this to be on, instead of tying the input to 5 volts, we're just going to tie it to ground. Notice now that the source is the higher voltage and the gate is going to be attached to ground. So what that's going to leave us with is VGS, which is equal to the voltage at the gate minus the voltage at the source, is now going to be, well, 0 volts minus 5 volts. And now you can see minus 5 volts is less than minus 2 volts for our gate source threshold voltage. So the MOSFET is on. Okay, so now you could go ahead and calculate all of your other stuff if you knew what your load was. You now know that this MOSFET should be behaving like a resistance of 0.1 ohms between the source and the drain. You can calculate your current going through there. You can figure out your voltage drops, your power, all of that. But the MOSFET is on when the gate is tied to 0 volts. If instead of 0 volts on the gate, if you tied this up to 5 volts, notice that now you would have 5 volts minus 5 volts, which gives us 0 volts. 0 volts is not less than minus 2 volts. So the MOSFET would be off, okay? So this is the reason for those abbreviations. This is why they'll abbreviate it this way. They put a little inverter bubble over here on the input. For an N channel, the abbreviation is, which is just inverted logic. So it is on when we have 5 volts over here. It is off when the gate is 0 volts versus a P channel. So essentially the only difference, well, we have to make sure that if we're using an N channel, we do high side switching. If you use a P channel, you have to have high side switching. If it's an N channel, you have to have low side switching. And the whether it's on or off is the opposite for a P channel. It's just going to be on when we have 0 volts. Okay? So that's a P channel MOSFET. Do you have any questions about that? Okay, so let's go ahead and let's look at another incredibly useful circuit using MOSFETs. And this was actually one of the examples that I gave on the first day of class. Okay, let's say I get a motor, and let's say that motor turns clockwise when I have 5 volts attached to the plus and ground attached to the minus. Okay, how do I make this motor turn the other direction? How do I make my motor turn anti-clockwise or counterclockwise? Any ideas? Switch the voltages, right? Exactly. Instead of having the positive tied up to 5 volts, let's tie this to ground, and let's tie the minus to positive. Okay, so that's how you make this motor turn in the opposite direction. You physically detach and swap and plug back in. Okay. How do I make a computer do that? Do I make some robotic arms that come out and actually physically disconnect the wires from the motors and flop them around and plug them back in? How do I do this with... I want a computer to be able to turn this motor the other direction. I don't want me to be able to turn it in the other direction. I know I can do it. I just physically disconnect the wires, swap them, plug them back in. How do I make a computer do that? Here's the H-bridge. Okay, so at the heart of this problem, what is it you're trying to do? Well, we're swapping the voltages to make it turn in the other direction so that we can cause current to flow in the other direction. So in this case, we wanted the current to flow down through the load. In this case, we wanted the current to flow up through the load. So really, what we need to do is come up with an arrangement that allows us to change the direction of current through a load. Meet the H-bridge. Now I'm going to set up a simple arrangement. I'm not going to invoke any Mosfets yet. I'm just going to create an H-bridge using a generic switch. Okay, so here's my H-bridge. Now this is referred to as a bridge because it looks like I have two parallel branches and I have something connecting the center of each one of those parallel branches to each other. That's where the word bridge comes from. H comes from, well, it looks like an H. Electrical engineers aren't that inventive. Okay, so what happens if I want current to flow in this direction? Well, all I have to do is close this switch and close this switch. And notice now my current goes from my positive to my minus, and the only path available to do that is through this switch and this switch. Both of these other switches are open. So the current's going to go to the right through my load. Okay, what happens if I want to change the direction? Say this load is a motor. How do I make the current go in the other direction? Well, let me go ahead and draw it right next to it. all I have to do if I wanted the current to now, instead of going from left to right, to make it go from right to left, all I have to do is close this switch. I leave this one open. So this one that was previously closed to make the current go to the right, all I have to do is open that one up and close this one instead. Similarly, I'm going to switch which ones of these are closed. This one's going to be closed. This one's going to remain open. Now my pathway for current to get from our higher voltage to our lower voltage is going to take the path of these closed switches. So now my current goes this way and goes to the left through my load and then goes down to ground. Clever, right? So with 4 switches, I can make that happen. I can make my motor turn both left and right by a computer. Now, obviously, I've drawn this with switches, and so a person would still have to, switch this and switch that and then open that and switch blah, blah, blah. Can I do this with MOSFETs? Absolutely. Now, notice I have a combination of low side switching and high side switching. Low side switching, high side switching. For the high side switching, I'm going to have to use a P channel for that reason that I discussed earlier in class. Both of these will have to be P channels for the high side. For the low side switching, I can just keep that as regular N channel MOSFETs. Now, if I want one signal to change everything, what I'm going to do is, well, I'm going to tie these two together, and I'm going to tie these two together, and then I'm going to give myself an inverter down here. And now watch what happens. When I have 5 volts here, is this one on or off? Help me out with this. 5 volts into a P channel MOSFET, closed or open? Just type it in chat. Five volts into a P channel. Covered it 10 minutes ago. Yeah, it's open. Okay, 5 volts into an N channel. Closed or open? Closed. Okay, 5 volts into an inverter. The output is 0 volts. I get 0 volts over here. 0 volts into a P channel. Open or closed? Closed. 0 volts into an N channel. Open. Sweet. Check this out. Current always flows from a higher voltage to a lower voltage. Current's going through that direction. Okay, what happens if I want to change the direction of the motor? In other words, what happens if I want my current, instead of going from right to left, to make it go from left to right? I just change this 5 volts to a 0 volts. 0 volts into a P channel is now closed. 0 volts into an N channel. It is now open. 0 volts turns into 5 volts. 5 volts into a P channel. Open or closed. Open. And 5 volts into an N channel, closed. Okay, now the current can get from our high voltage to our low voltage, but it's got to take the different path. So depending on if we gave it 5 volts, we'd get the current going to the left, and if we gave it 0 volts, the current would go on the green line to the right. Okay, so incredibly valuable circuit. This circuit is very, very useful. Not just for motors, but you can use Hbridges anytime you want to change current direction through something. And so you'll find that this topology, this Hbridge, gets used for lots of different switching circuits. In the case of making a switching power supply, you'll see half of this used. So this circuit, arranging it such that you can turn the top side on and off, ends up becoming incredibly valuable. Let me show you. This is, if we have half of an Hbridge, we have a half Hbridge. All right, I'm going to do the first in red. And we can look at this from the perspective of V in and V out. Let's put 5 volts here. 5 volts. Is the top MOSFET open or closed? Top MOSFET, open or closed with 5 volts going into it? Open. Okay, 5 volts going into an N channel. Open or closed? Closed. What is V out? What's my voltage on V out? Yeah, it's directly connected to 0 volts. Should get 0 volts out of there. Okay, the 5 volts is disconnected. All right, let me switch up colors here. Do this in blue. Okay, instead of putting 5 volts on the input, let's say I put 0 volts on the input. 0 volts on the input. Is the P channel closed or open? Closed. 0 volts into an N channel. Open or closed? open. Okay, what's my voltage output? All right. What works this way where I put 5 volts in, I get 0 volts out. When I put 0 volts in, I get 5 volts out. When I put a high in, I get a low out. And when I put a low in, I get a high out. Inverter. Okay, this is awesome. This is what's inside of your inverter gate. I promise you. It is just this. A P channel with a Mosfet, with an N channel below it. Can I construct all of my digital gates this way? Absolutely. Let me go ahead and pull up a browser. And gate. Let me type in and gate Mosfet. Here's an AND gate. If I want them both to be, if I want the output to be high when both inputs are high, so if both of these are high, well, I'd have to draw that out. I'm printing it right now. Well, let's say A is 1 and B is 1. Well, a 1 going into, let's see, a P channel over here. That's a high going into a P channel. So this is open or closed? It's open. Okay, same thing over here. A high going into an N channel. This is closed. Okay, this B1, this is going into a P channel. This is closed. Sorry, open. And a 1 going into an N channel is closed. So that means I have a low over here, and we already did this one. This is just an inverter over here, so 0 turns high. So with all 1s on my inputs, I get a 1 on the output. If any one of these are, if I switch one of these, let's go ahead and make this to be 0. Now this one is closed. And with this one being closed, this one is now open. I have disconnected the pull down network. I have connected the pull up network. This 0 now turns to 1, and the inverter changes that into a 0. Okay, that's my AND gate. Okay, so all of our gates are constructed out of MOSFETs. In fact, all of our digital circuitry we call CMOS. Complementary metal oxide semiconductors. Metal oxide semiconductors, MOSFETs, MOS. Okay, they're semiconductors and they're formed using MOSFETs, which are constructed with a metal oxide layer between the gate and the body of the transistor. And complementary. Complementary because we have a corresponding pull up for a pull down. We never leave this floating. We either have it tied up to 5 volts or we have it tied down to 0 volts. Same thing with our AND gate. We either always have something tied up or tied down. So over here you can see we have a pull-up network here. We have a pull-down network over here, followed by another pull-up network over here and a pull-down network over here. A complementary pull-up for every pull-down, constructed using the technology of MOSFETs or metal oxide semiconductors. Okay, so that's where our digital gates come from. Kind of cool? Yes, amazingly neat. All of our gates. So let's go ahead and instead of an AND gate, let me pull up a NAND gate. Okay. Did you ever hear that a NAND gate and a NOR gate is more fundamental than an AND gate and an OR gate? Did you guys learn about that? That you can make any logic out of NAND? Yeah, and NOR? Okay, here's the reason for that. This is a NAND gate, a not AND gate. Here's an AND gate. Notice an AND gate is just a NAND gate followed by an inverter. So even though the symbol, when you're writing it out and you're doing your digital logic and you're writing out your Boolean algebra and blah, 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 all of that stuff, even though you probably mentally think that an AND gate and an OR gate is more intuitive and it's simpler because you don't have that extra negation, but from a hardware level, that's a whole nother 2 transistors that you need to put at the end, and you have to follow it up with an inverter. Whereas a NAND gate has no inverter stage afterwards. So a NAND gate is more fundamental from a hardware perspective. It has less parts. And so you can cram more of these onto a piece of silicon than you can AND gates. And so when you go through Xilinx, Xilinx, it's going to do its own optimization and it's going to reduce everything to the lowest number that it can. Now, granted, it's probably a bad example because Xilinx uses lookup tables for all of the logic that it implements in an FPGA. But if you're talking about actually synthesizing for a physical layout and you're constructing the actual MOSFETs on a piece of semiconductor to make an integrated circuit, then you want to use the least number of MOSFETs possible. So any type of synthesis should be able to reduce it down into, that universal gate or the fewest amount of logic gates needed for your desired digital circuit. Okay, so I just wanted to go ahead and spend some time on that. We don't have time to get into that new part. That's fine. The op amp. What we'll do now is I'll take any questions. I'll pause. I'll stop the recording. I'll take any questions, and then we'll be able to work on the what's that called? The common emitter amplifier lab, and using the MyDAC in order to act as the function generator and the oscilloscope. And we'll do that during lab today. It is, I believe it is due next time? Oh, now I can go ahead and yes, digital circuits are made from analog parts. We can't ignore the analog. Okay, so we have today to work on the lab, and then we also have Monday to work on the lab, and then it's just due by the next day. Okay, so we'll go ahead and finish that up. Don't forget, we also need to get some LM358s. So between the resistors you already have, between the capacitors you already have, the transistor, the 2N3904 that you're using, and an LM358, we can actually do some pretty cool things at this last part of the semester using the MyDAC that everyone should have by now. Okay. Yeah, I did Tuesday 11:59 p.m. Because if I put 12 a.m., then maybe people get confused with nighttime or lunchtime. And then so I just wanted to give everyone the most amount of time as possible. Everyone said they'd be fine with 3 lab periods to do this, to do the breadboarding part of this. So, yeah. Okay, so let me go ahead, stop recording.